everyone, and welcome back to the Towards Data Science podcast. Now, it's no secret that AI scaling has really taken off. Ever since GPT-3 came out, it's been clear that one of the things we're going to need to do to move beyond narrow AI and towards more generally intelligent systems is going to be to massively scale up the size of our models, the amount of processing power they consume, and the amount of data they're trained on all at the same time. And that's led to a huge wave of highly scaled models that are incredibly expensive to train, largely because of their giant compute budgets. But what if there was a more flexible way to scale AI, one that allowed us to decouple model size from compute budgets so that we could track a more compute efficient course to scale? That's the promise of so-called mixture of expert models, or MOEs. Unlike more traditional transformers, MOEs don't update all of their parameters on every training pass. Instead, they route inputs intelligently to submodels called experts, which can each specialize in different tasks, and on a given training pass, only some of those experts have their parameters updated. Now, the result is a sparse model, a much more compute-efficient training process, and a new potential path to scale. Now, Google in particular has been pushing the frontier of research on MOEs, and my two guests today in particular have been involved in pioneering work on that strategy among many others. Fedus and Barrett Zoph are research scientists at Google Brain, and they join me today to talk about AI scaling, sparsity, and the present and future of MOE models on this episode of the Towards Data Science podcast. I'm really excited to have this conversation, especially with both of you. You know, the space that you're exploring is such an interesting one, and it's at the intersection of so many critical trends really in AI today, both the scaling piece and the mixture of experts piece. We're going to get to all that stuff in a minute, but I want to start with a situating question here just to understand what brought you both to this space to begin with. What prompted your interest in AI, in scaling, in this whole story that you're now exploring? Maybe I'll start with Liam first.
Yeah, I've had a background in sort of physics and both finance. And sort of one common theme was sort of these like predictive questions. How do we make better predictions, whether it's like identifying like what particle is this in the CERN accelerator, or, you know, predicting some aspect in like, you know, a financial market. But honestly, the most interesting aspects were like, okay, what's behind these sort of predictive algorithms and the machine learning? And I realized like if I want to actually study the most like interesting ML, I should just be doing it in that field. So been studying machine learning for several years now. I've sort of switched between generative models, reinforcement learning. But honestly, like I think just the progress and the promise of scale has just been like, you know, too incredible. So that sort of like, you know, caused me to gravitate towards this. And, you know, as we'll talk about later, I think sparsity and sort of adaptive computation is a really important and like essential aspect for sort of scaling up these models into the future.
Awesome. And Barrett, maybe same question to you, so we have a sense of who you both are here.
Yeah, so actually when I was an undergrad, I got really into working on machine translation, but this was kind of before like neural machine translation. So I worked a lot with like, you know, phrase-based and syntax-based machine translation. And actually, when I was working on this was kind of right when the sequence to sequence paper came out. And then there was kind of this big shift from like kind of the standard statistical methods to some of the deep learning methods. So that was actually kind of how I first got really, you know, excited about a lot of the stuff in the field. And then from there, I actually ended up joining Google on the Brain team. And I've worked now on like kind of a wide variety of things. I've spent like a lot of time working on neural architecture search, computer vision, data augmentation, but yeah, most recently on kind of large language models and ways to make them a lot more efficient, such as sparsity. So yeah, I'm very excited about the space.
Yeah, and the scaling space, of course, has exploded, almost literally exploded in the last few months and years. And there is so much going on there. I think it can be hard for people to keep up. I think most people have a vague sense, though, of what scaling is and how it leads to generalization. That might be helpful to start there, though. But one thing that people are definitely less familiar with, or at least I am, is mixture of expert models and how they factor into the scaling story. What is your version of the scaling story? And then where do mixture of experts models come into that story?
Kaplan et al. In 2020 sort of uncovered these like really nice like power law scaling dynamics. Basically, the training loss, or sort of this like held out loss even, of these like very large scale models scales in a very predictable manner if you add more compute, more data, and more parameters. So this has sort of been like really kind of been the backbone and support of these insanely large models because they're expensive, but there's like this nice predictability. So people are like comfortable putting behind like millions or tens of millions of dollars behind training these models. However, these can be like very expensive. Like the idea behind some of these like larger scale like transformer models is anything that comes in, any input is going to touch every single parameter. So this can be sort of like computationally wasteful. So no matter whether it's an easy example or a difficult example, you're going to be using the same number, the same parameters. What Mixture of Experts does is it's sort of looking at these models and it's sort of adding in specific layers. And what you're doing is you're sort of almost replicating a specific layer many different times, and we call these experts. So an expert might be a single matrix multiplication or maybe like a stack of multiplications, but it's basically just sort of like often mimicking or mirroring the original sort of like component inside the dense model, and you replicate it. And now what's different about a mixture of expert is as an example is coming in, it's going to be sort of either split up into like words or maybe like the full example is going to be sent to specific elements. But each of these sort of elements is now going to be routed to a specific expert. So we look for some sort of specialization. We look for an element like that is like best suited for each expert. And then you sort of do this aggregation and you sort of proceed as before. So the idea of the mixture of expert is we can produce these like much larger models. So we can increase the number of parameters dramatically, but we're actually holding the computation completely fixed. So we're still doing the same amount of computation as before, but now we're actually selecting which parameters to use.
Yeah, I think that's like a great explanation. So yeah, I think kind of sparsity adds like another axis for kind of scaling these models. Whereas before, when people are scaling models, the computation per input and the number of parameters is kind of scaling together. But now we can kind of decouple this and keep the computation per input fixed, but scale the number of parameters. So it's kind of like an interesting factorization for kind of the two ways to add more like scaled models, which is, the computation per input and then the number of parameters.
And Barrett, what have you observed in terms of the actual sort of specialization characteristics of these experts? Are you able to peer in and notice like, oh, this expert really is specializing in all things automotive, maybe in this speech generation model, whereas this one is maybe more food related stuff? Or does it break down neatly along those lines, or is it more ambiguous?
Yeah, so this is a really great question, and actually something we recently looked into in our last work. And surprisingly, actually, yeah, you can see some levels of specialization and actually even some like kind of relatively trivial boundaries. So for example, there's like an expert that will specialize more in punctuation and another that might specialize more in like proper nouns. So you actually do see this by just training the model. So like kind of, yeah, the optimal way for this model to be sending the tokens through it, the way it learns through gradient descent is actually, yeah, to kind of specialize these tokens across different experts in kind of, pretty easy to see ways.
That's actually really interesting because I would have thought of something like punctuation or parts of speech recognition as being a kind of universally valuable thing that would apply independent of, say, topic. Now I'm using the word topic very loosely to refer to like what humans might think of as topics. But it's interesting that the kind of grammatical function, which again I would have thought of as this generally useful thing that maybe every expert would need on some level, ends up getting specialized in these different experts. Is that, I guess, does it make sense to you that I'm confused about that, or is there some obvious reason why it doesn't?
No, I was like, actually quite surprised. Oh, go ahead, Liam.
Yeah, I mean, like as Bert was sort of saying, like these concepts are insanely shallow. Like when you sort of pose the question, you're like, oh, is there an automotive expert? And we're like, no, we actually have something that specializes in capital letters or punctuation. Right. It's like very, very shallow. Yeah, I agree. It was sort of surprising to us. I think we were sort of expecting like maybe a deeper or like more semantic level of specialization. There were like some things that were slightly deeper. So for instance, like numbers were sort of like a concept that like some experts would specialize in, both through like written numerically as well as like spelled out in English. So like the number 2 versus like 2 spelled out like TWO. So there's like, a slightly higher level. Another really consistent specialization was our models that we've been training are fill in the blank models. So you take some like a sentence, you blank out certain sections, and it sort of fills it in per the context. These blanks are represented by special tokens, and we almost always consistently see an expert specialize in these like blank tokens.
Okay, so task level specialization.
I guess like the task is sort of fill in the blank. But yeah, like if we're actually mixing in a bunch of tasks, I suspect that would also hold. So if we were doing sort of a batch of examples, some of which are fill in the blank, some of which are predict the next word in the sequence, I suspect we would still see this specialization, which would sort of indicate or support task specialization.
And how many experts are we talking about here? Because like when we look at ensembling, for example, like old school, random forests or something, there's this process of parameter tuning where you're thinking, okay, how many estimators do I need? How many decision trees do I get together in my random forest? And how does that kind of influence performance? Are there a similar set of considerations when it comes to these sparse models? Like how does number of experts affect the end result?
Yeah, so this is a great question and something we actually spend a lot of time thinking about. So yeah, so I think there's right now it's a very, we kind of base the decision off of a few things, one of which just the empirical performance, like you actually typically just have to try running the model, maybe with a few different number of experts just to see how it performs. And then also we typically co-design it with the hardware. So one thing that we kind of do is like, per machine, we basically only want one expert most of the time. And so a lot of the times, depending on how, many machines we're training on or like what's the distributed setup, that'll actually really help us guide the number of experts.
Oh, interesting.
I think in general, we find that you do get diminished returns after, going from like 256, 512, 1024. For most of our recent work, we had like 64 or less experts. So yeah, I think we kind of err on actually the side of like having less. And we've actually also seen it to be beneficial even if you only have two experts. So, you don't actually really even need a supercomputer to kind of get the benefits from something like this as well, which is pretty exciting.
So it almost makes you think of dense models as like one end of a continuum of mixture of experts model, really. Okay.
That's exactly right. Yeah, and I mean, like, I think some of our earliest models, we were like, very enthusiastic about sparsity, and some of our models were designed with thousands of experts, which trained and gave very good pre-training speedups. But when you sort of have models that have like so many experts, you can then start getting like strange transfer properties. So like Barrett was saying, like I think we've sort of consistently kind of like honed in on like fewer number of experts where you're still getting like a very good pre-training speed up, but you don't have these like strange like adaptation problems. So we've, like Barrett's saying, like 64 experts or less has been very good for like the kind of hardware we've been running on.
Okay, that's really interesting. So one of the cool facets of this seems to be this entanglement between the architecture of the model and then the architecture of the hardware, which seems to be a really big part of the scaling story as machine learning kind of becomes software engineering or becomes some kind of engineering. I'm not exactly sure what kind it is, but it's something. So is this a domain where you would expect like custom ASICs to come in, where you'd expect like more and more kind of MOE specific hardware to be developed, even if this goes further? Is that on the horizon? Is that possible, or do you think it's way too early to speculate at this point?
Yeah, so I think from a speculative standpoint, I think something could absolutely be done. So when you're looking at distributed transformers, there's these certain communication collectives that are very frequently used, like reduce scatter and all gather. And this is kind of how the communication primitives work for like data parallelism and even like, model parallelism. But experts actually introduce a new communication primitive, this communication primitive called all to all, which isn't seen in normal like standard dense distributed transformers. And so, at a high level, it's basically like, yeah, actually these sparse models introduce this kind of new communication collective like primitive that's not typically used. So like being able to speed up that more could disproportionately benefit sparse models going forward. And this is introduced because, when you're routing tokens, you need to be able to, send any token to any of these experts. So that's kind of where that's being introduced.
Interesting. Okay, so yeah, it seems like this is, I mean, again, highly speculative, but could be an entire rabbit hole for hardware as well as architecture. That's really cool. And now, one area that you've identified in your research on mixture of expert models is this idea of training instability that seems to be a particular problem for MOEs. So I'm curious if you can describe like what training instability have MOEs historically run into, and what's the cause?
Yeah, I think fundamentally, it's a more unstable system because if you sort of like think about what's happening as you're sort of like doing a forward and a backward pass through the model, in a dense model, you're doing the forward pass, activations come forward through the matrix multiplications and get some output, and then we're coming backwards, and you're going to have like some small changes to the parameters, but it sort of keeps it like in the same space. So like for instance, like an incoming activation where the weights haven't been updated dramatically are probably going to produce some small perturbation on the outputs. So you have like some sort of like smoothness property. For mixture of experts, now we have these like very strange results. So for instance, if an input is coming in at like time step t for the model, where t represents like the current state of the parameters, it might get expert I. So input comes in, it goes to expert I, and then you produce some output. But now let's say we're looking at t+1. So the parameters have shifted via the gradient update, and the same sort of input, the same example is coming in. Now it might actually get sent to expert J, and expert J might have a very different output. And so you sort of fundamentally have these like kind of very discontinuous systems. So a small little change can actually now like shift the output dramatically. And then again, as sort of like looking into the details of these models, there's these sort of exponential functions introduced through these like softmaxes. So these softmaxes are determining where should this token go. So we produce a probability distribution over the available experts, and then we select top 1, top k, and we send those out. These exponential functions, when sort of mixed with low precision number formats like bfloat16, can produce like really high round-off errors. And so every time we introduce an expert layer, we're introducing some of these exponentials. And so this can sort of like exasperate things as well. So it's just sort of like a fundamentally like kind of very different type of model. And all large scale models seem to have like some sort of like training instability issues, but our case seems like particularly fraught for these issues.
Yeah, that discreteness seems to be an important aspect of this in the sense that, well, correct me if I'm wrong, but any discrete component makes backpropagation much harder because there's no gradient to follow. So in some sense, the model isn't continuously improving, essentially.
Yeah, we have some gradients back to the gating function. So we're sort of multiplying the output of the expert that was selected by the probability that was being selected. So now we're going to have a gradient pulling back to the router here. But yeah, there's definitely like some discontinuities, and these again, this like sort of interface and like all these extra exponentials can really destabilize models.
Okay, and Barrett, part of your research looks at when you look at this instability, you look at the trade-offs between instability and performance, and they kind of seem to be linked somehow. Can you just describe what that link is and why it exists? Like, why would instability in training be linked to performance?
Yeah, so this is a really good question. So when we first kind of encountered these instability issues, we tried a really kind of wide variety of techniques to try to fix the instabilities. And we did notice this very clear trade-off between techniques that would fix the instability but hurt the quality. And yeah, we kind of did find this like almost fundamental trade-off between some of these things. And yeah, so why does this exist? I think is a good open question almost. I think in some sense, a lot of the ways you fix the instability is by slowing down training, by having smaller updates, constraining gradients and things like this, which, you could kind of see hurting quality because it's just slowing down the training. Another class of techniques that we experimented with that also we found to really help the instability was like injecting noise into the model. So like using dropout and like some other techniques in this realm. And when you're, adding noise to the system, that also hurts the quality. So it was kind of those two avenues that we spent a lot of time exploring, both of which, hurting the pre-training quality, but allowing us to kind of fix the instability, which was kind of a very interesting trade-off that we noticed.
One thing that we sort of identified were multiplicative interactions in these models really seem to sort of like improve the quality, however, at the cost of stability. So like there's like two examples of these multiplicative interactions in standard transformer models. One is sort of these like element-wise products of in like the scale parameters. So for instance, like you'll do a normalization on the logits or normalization on a particular layer, and then you're going to do it element-wise multiplication by a set of like scale parameters. This is then not accompanied with like a reduced or like a summation as you would with like a matrix multiplication. Another instance is sort of like kind of Gelu linear type approaches. So there's a transformer that consists of like self-attention blocks followed by feed forward blocks. These feed forward blocks are often just like input matrix, which splays out to like a larger hidden dimension, and then an output matrix, which reduces it back to the same D model. You can alternatively sort of do a set of input matrices. So like you could have like two input matrices or multiple input matrices, and you could do element-wise product on those as well. Again, you don't have this like same summation as you would in the matrix multiplication. And we find that both these techniques dramatically help the model, but at the expense of instability. And I think, there's been like a lot of speculation about like, multiplicative interactions like LSTMs, like, going way back, as well as like, in transformers. So I think some of these like kind of higher level like multiplicative interactions have been, very valuable, but maybe slightly more unstable.
Okay, so this trade-off does extend then into more traditional dense net transformer type setups as well. Actually, that does make me wonder, like, if somebody's trying to decide if like you're about to run a massively scaled operation, you're trying to decide between a switch transformer or a mixture of experts model and a dense net. What are some of the factors that you think should come into play in making that decision? Like, do we know enough to make an informed choice there, or is it still very up in the air?
I would say, yeah. So one thing I also wanted to kind of add to the previous question was we actually did find a technique that was basically pretty much able to alleviate all of our instability techniques without really hurting the quality. So yeah, I think from that standpoint, is there a fundamental trade-off? Probably not, but it's just sometimes really hard to find the correct method. And I also wanted to leave that, on a more optimistic front, that I think, large scale sparse models can be trained stably, especially, after a lot of the good research that's come out recently. In terms of the, like, when should you choose a dense versus sparse model is like a really good question. So one thing that's kind of, I think probably is the biggest consideration is like how many machines you have to train and then serve your model. So on a per parameter basis, dense models will always outperform sparse models. They're just like not as efficient on a per parameter basis because, it's like each input can have different number of parameters. It's just not that efficient of a setup. So when you're very constrained for, the amount of machines you have, especially to like serve your model, then it would be definitely very good to be using a dense model over the sparse model. I think sparse models really shine when you're training your model and you're using like a lot of data parallelism. And, when you're serving the model, you have like higher throughput. I would say those are kind of like the two key regimes that allow sparsity to really shine over dense models.
Does this have implications for like open source? Because you think about something like Alether AI, where they're scaling dense nets basically at 20 billion odd parameters at this point. Do you see this as maybe, unfortunately, like a little bit less compatible or less easy at least to share on the open source side, given that you do have kind of this hardware constraint?
Yeah, I definitely think that could be the case, at least, unless you do more, maybe interesting ways of hosting the model, like, you are swapping parameters out to CPU or things like this. But yeah, naively, it's just if I give you a model with, 200 billion parameters, it's just hard for, I think, a lot of people to use it if you don't have the machines to host all the weights.
Okay. And what about this? So obviously the goal of scaling to a significant extent is generalization, right? Like that's really the holy grail here. I've seen, or I've noted in some of your work that historically it seems like mixture of experts models have struggled a little bit more with generalization. I'm curious about why that is. Like, why would it be harder for MOEs to generalize than for dense nets?
Yeah, it's a great question, and this is something that Barrett and I have thought about for at least a couple of years now. Yeah, to our dismay, when we first trained our like largest trillion parameter switch model, we found great pre-training speedups over the then state-of-the-art like T5 XXL model, which was like the largest and state-of-the-art like encoder decoder model at that time. But then when we were fine-tuning, like say on Superglue, a task to sort of test like classification and reasoning, it was actually quite poor. and we were kind of confused by this. I think one of our hypotheses right now is that these models are sort of prone to overfitting. It kind of stands to reason just because we have so many like degrees of freedom because of all the parameters introduced. One consistent trend we've noticed is sort of like under a data distribution shift, say we go from pre-training to fine-tuning. So we're adapting the parameters for a specific task. Whether the task is large or small, the optimization of the MOE or the sparse model appears to still be faster than the dense model. So we don't think it's an optimization issue. However, for some of the smaller tasks, we frequently would find that the generalization, so like held out data, would not do as well. So this is sort of like hinted to us, and like there's sort of been like other data that we've seen that maybe overfitting is a problem for some of these models. And so we've spent a little bit of time thinking about like regularization or updating like only like subsets of the parameters. But I think this is like, one kind of fundamental question.
And what does
with so many degrees of freedom, it's easy to overfit.
Right. So what would regularization strategies look like in the context of an MOE model? Like, are there specific hacks that you need to think about because of the architecture?
Well, one hack is we increase the regularization or the dropout inside the expert. So like the experts sort of have their own like hidden dimension, and you can sort of selectively increase the dropout within there. That seems to be like one approach. And we've also tried like, more exotic things as well. I don't know, Barrett, you want to comment on some things?
Yeah, we actually experiment around a lot with these different techniques without really any success. So we played around a lot with like, oh, can you drop out, some specific experts during pre-training? So like in a batch of tokens, like dropping out some experts. We also played around with this during fine tuning. So things along that nature of, for a batch of inputs, don't allow them to have access to all of the experts, but we couldn't get anything like this to really work well.
One thing that a mixture of experts models really do make me wonder about too is, we touched on this a little bit, but this idea of interpretability. When you have these maybe somewhat well-defined, again, it's unclear how well-defined, but when you have these relatively well-defined experts with specializations, that makes me wonder if we should be optimistic about the prospect of more interpretable models where we can say, okay, we're thinking about maybe not automotive tech, but instead punctuation. We at least know which model to look at for that. Is this a facet of this? Is this a potential advantage of mixture of experts models?
I think it's quite plausible. Because yeah, as you said, now we're not sort of looking at all these sort of like soft features. We're not just looking at, sets of numbers. We can actually see these like discrete decisions. In this context of the sentence, where did this word go? Which expert handled it? Right. And yeah, I do think it sort of like allows for some more interesting interpretability work. We have only scratched the surface there. So, the simplest thing being like, well, where are the tokens going? But, there's a lot you can do there. Trying to understand the token routing in the context of the sentence. So right now, it's sort of like not a very accurate picture to say like, oh, this word gets sent to this expert. Because really the word, by the time it's sort of like, many layers deep in the model, isn't just a representation of like that word. It's not just a word embedding. That word, that vector has sort of been built up on the context of the entire sequence. So some interesting interpretability work might be like, okay, how does the word doctor, like, at that like time step, get routed based on like preceding or like, following text, right, if it's like in the encoder. So I think this is sort of like, an interesting element where you could sort of like explore like maybe like bias or some of these elements. You could also do like kind of stranger things where it's like, you might see a specialization and you could consider then like extracting an expert at inference time, or maybe like in the future, you can sort of like add experts, like you try to make it like more of like a plug and play model. This is definitely more speculative, but I think, this allows for, an additional level of interpretability not present in standard dense models.
Yeah, it also makes me wonder about this idea of inductive priors in deep learning. Because to some degree, I mean, you could tell the story. One way you could tell the story of this approach to kind of more and more general systems is to say, oh, well, this whole time, really, we've been relaxing more and more assumptions about the architecture of these models. Classical AI, we have like random forests with a very specific kind of data flow through our system. And we specify all this. We tell the data where it's going to go. Then we move to deep learning and feed forward networks, and then convolutional networks that kind of make some assumptions about the translational invariance in an image, and then we encode that in the architecture. So we take our human priors and we kind of stuff them in there. And then transformers seem to unify, convolutional nets and LSTMs and those threads. So it seems like we lost a lot of those inductive priors. I'm wondering about how to place MOEs in that context. Like, are MOEs, is this an additional assumption, an additional inductive prior that we're adding when we say, oh, we'll have a routing mechanism and different experts? Or are dense nets like a special case? Are those the inductive prior? And actually, MOEs are kind of a further level of abstraction.
Yeah, I mean, I think it's an interesting question. I mean, like we were talking about before in our scaling plots, the special case is basically a dense model, right? So you start reducing the number of experts from 8 to 4 to 2 and then to 1, and it's just like, well, this is essentially equivalent to a dense model. So yeah, I mean, it's sort of interesting. Like, I mean, you could maybe think of this as like a relaxation, but I mean, like, there are like a lot of sort of like specific priors and like, how are we doing this routing, like top K, like this sort of like layering. But I think like, so in like some sense, it feels like a tighter inductive bias, but like in others, it's almost looser where it's like, well, I'm not forcing the model to sort of use the same parameters each time. Like, I'm allowing it to sort of like, select and in like an adaptive way, which parameters to use. My suspicion is like, we're going to continue to sort of like evolve these models. Like, this current like implementation is probably not like the end all of this, but yeah. So I don't know. I guess it kind of depends on your perspective a bit.
I would say I definitely err towards more that we're kind of removing this kind of prior on, where before all the inputs had to have the same weights, and now actually we're kind of breaking that assumption. Like, while we definitely do introduce some, new biases by, the way that the routing algorithm is done, so forth, so on. But actually, in our experience, we found that like a lot of different routing algorithms actually perform pretty similarly, which makes me believe that, yeah, it's not too much of a bias, at least from the specific way we're doing the routing. But yeah, I definitely just kind of view it as a very natural trend where before each input gets all the same weights, we relax that. And then I think the next natural relaxation is also that, each input just allows a different amount of compute to happen on the input as well. So I just kind of view it as maybe the natural progression of how these models might go.
I remember thinking this as well when it came to just like plain old feed forward neural networks. I kind of thought like, well, that's it. I mean, it's a bunch of multiplications. Anything can happen. Like, there's nowhere else to go. And anyway, it's always interesting to see like all those little assumptions that we find ourselves making without realizing it. And so often it seems like the history of machine learning is to kind of zoom out and go, well, wait a minute, that was actually something that we coded in ourselves. It doesn't have to be like that. Sort of interesting, especially because I think a lot of these intuitions come from locking into certain assumptions that have to do with biology, where neural networks, of course, are inspired by the structure of the human brain, at least at a loose level. I wonder if there's something to that here. Obviously, none of us are neuroscientists, but is there a sense in which this draws inspiration from like maybe the specialization of different components of brain structure? Have you guys thought about that at all?
Yeah, like you said, I am not a neuroscientist, nor Barrett, but from a 30,000 foot view, it's like, yeah, I mean, now, like, our brain, from what I've been told, doesn't use every neuron, every synapse for anything
Right.
we're doing, right? Like, if I'm recounting my name to you versus like solving a math problem versus coding versus like on a walk or playing tennis, like it's like, dramatically different like paths being active. So from that like very fuzzy perspective, it's closer. But like, for many other like aspects, like sort of like feedback mechanisms, recurrence, like all these other aspects, it looks nothing like a brain.
And was it inspired by that sort of thinking, or no? Okay, so pure, like, we're in pure engineering land at this point. Like, what can we do with our matrix multiplications to? Okay, good.
That's right. Yeah, just hardware driven.
I always love to talk to people who are working in the space because they draw inspiration from so many different areas to kind of inform their thinking on this. So it's interesting to hear that like biology is just not at all kind of a focus right now, and more so on the engineering side. As we look ahead now to something more like general intelligence, which obviously, as we've said here, is more and more in focus. Do either of you see mixture of experts playing an important role as we move towards that? Not that we're going to be seeing switch transformers explicitly in HAL or in AGI, but like is there a sense in which MOE has a role to play, do you think, in the long-term future of AI?
Yeah, I mean, I'm very, I think, bullish on the fact that every input won't have the same parameters. So I think from that standpoint, I think that kind of paradigm will be around in the future. In terms of like if the way we're currently doing it now or like these learned routing mechanisms, I really don't know. But yeah, I think definitely the paradigm of different inputs can get different subsets of weights makes a lot of sense to me. And I would be surprised if the models in 5 to 10 years from now don't have that.
Strongly agree. I mean, I feel like it feels very natural and obvious to me that in the future, our models will sort of have like, a much greater degree of adaptivity, whether it's sort of selecting parameters, selecting compute, like maybe other sort of like adaptive aspects. But yeah, like, I mean, right now it just feels like we're sort of like wasting compute, or maybe we're under computing in some aspects, depending on like what's coming in. So yeah, I definitely think the future is adaptive. Mixture of experts, like, I don't know if this is sort of like, the exact implementation, but something in the spirit, I think will probably hold for like, creating like really general and intelligent systems.
Very interesting, and again that flexibility coming up. As a final thing, I'm curious for people who are thinking about doing research on mixture of experts models, implementing their own even. What are some of the design principles that you've identified over the course of your research that might save people a lot of time? Like, what are some low-hanging fruit that you can do to make sure you don't make obvious mistakes when you're teeing up your MOE?
So I guess at a very high level, I would say, there's actually now some open source repositories. So maybe start with something that works as opposed to trying to implement something from scratch. Could potentially, really save you a lot of time. I always think it's easier to like start from a working system and then adapt versus kind of trying to build up from the ground level, especially due to some of the intricacies and little like technical details here or there. But yeah, in general, I would say start small, start with a small number of experts, start with a smaller model, and just kind of try to build up intuition at the smallest scale possible, and then kind of grow, test your algorithm as things progress. That's kind of my, I would say, baseline advice for people that are interested in tinkering with these models.
Cool. Liam, any tips at your end?
Yeah, I'd say question everything. Like, don't take it as gospel, like, oh, this is how we're supposed to do this, and this is like the only right solution. Yeah, maybe like one problem is like, some paradigm will be successful, and then people are only kind of like tweaking like small things like this, and maybe it reduces like the required exploration. So it feels like, yeah, like question like all the different aspects, like maybe like we're kind of in like some like, local min of like how we're sort of doing like our specific like design. But yeah, I mean, like, I think Barrett's advice is like, very solid one. Like, start small, make sure things are working well, start with like, some working code, understand how that works. But yeah, just question all aspects of it. Like, I'm sure there's a lot of blind spots that Barrett and I have probably missed.
Yeah, that's really spoken like people who've seen a field from the very beginning, and you just see how many decisions you just have to kind of make for the sake of making a decision. I imagine it was just a huge number, right? I mean, no one's ever done MOE before or at this scale, and you're just having to like take an intelligent guess, hopefully.
Yeah, I mean, absolutely. Like, like for instance, like Switch came out from this idea that's like, it was sort of predicated on, oh, you need at least top 2 or more for this like sort of expert selection, meaning like a token or an example had to go to 2 experts because it was sort of essential to sort of have this like comparative operation. Was expert 1 or 2 better at processing this example to give like a meaningful gradient? We just sort of broke that assumption, and it still worked fine.
It's scary how often that sort of thing happens, and you kind of go like, okay, well, I guess that entire subfield is no longer Very cool. Well, thank you both for this really fun conversation. I hope this is going to be useful actually for a lot of people, especially as we start to zoom out from the dense net world and consider more possibilities and more options. There's a lot of fun, guys. Are there places where you'd recommend people go to follow your work on MOEs or more broadly? Maybe your obviously team at Google Brain is doing a lot of cool stuff, but any blog posts to recommend there?
Perhaps we should write some blog posts. So yeah, I feel like it's still a new field for sure. Yeah, so I mean, there's like a lot of recent work, so you can kind of trace like citation graphs of like things citing like Noam Shazir's work, like outrageously large models, and some things sort of like citing some of the larger like transformer expert models. But yeah, I mean, the field's really exploded. It's going to be hard to get like the high level perspective, but yeah, read some of the recent work. But I actually don't know of a good survey or blog post right now. I don't know, Barrett, are you familiar with one?
I think I might have like one or two saved, but I don't know what they are off the top of my head. So maybe I can share them offline.
Yeah, that'd be great because no, but you're both totally right. I mean, there's always this awful lag between the cutting edge of the field and then when it kind of gets pre-digested enough for people to kind of go, oh, okay, that's what this variable means or whatever.
Yeah.
So I appreciate the the extra legwork there for that interpretability. Well, thank you both so much. This was a ton of fun.
Well, cool. Thank you, Jeremy.